Okay. So the question is, what values of X is this expression equal to 0? Now, some people wanted to expand that and did a nice job of it. Okay. And then solve the quadratic equation. Now you got to recognize it's a quadratic equation, so you can use a quadratic formula. Here that or factor it so you can solve it from this form. Okay. So there are two issues there that I'll mention. The first one, we're really trying to move toward locking in the idea of how you graph polynomial functions, understanding how they work. Okay, so we have this equation, x minus 5 times 6x plus 10 equals 0, which is what we get if a was 5, b was 6, and c was 10. Okay. This is 0. Well, if this is 0, you're going to get 0. If this is 0, you're going to get 0. And that's the only way it's going to be 0. We got to be sure we really understand that. You can't multiply two numbers together and get 0 unless at least one of them is 0. And if at least one of them is, if one of them is 0, then the whole thing is 0, because we can multiply by 0, you get 0. Okay, so this tells us that x equals -5. Or x equals -5/3. And I'm not going to go through the detail at this point of solving this equation or this equation, because I think everybody knows how to do that. I certainly hope so. Okay. So one thing we can immediately do about graphing this thing, because that's the next step. Okay, what do we now know about the graph of this function? Now, when you graph a function, what's the first question you ask yourself? Okay, graph. The intercepts. Okay. Well, the intercepts on the x-axis occur when y is 0. Now you simply have to lock that in. Okay. X-intercepts occur when y is 0, y-intercepts occur when x equals 0, and make sure you understand how that relates to what it relates to the graph. Why is that? Because everywhere on the x-axis, the y value is 0. Everywhere on the y-axis, the x value is 0. We understand that. Okay. X-intercepts occur and y is 0, y-intercepts when x is 0. Okay, so y is 0. Well, y is this expression. You know, I could put a y equals 3. Expression is going to be 0 when x is -5 or -5/3. So let's say we have -5 here, or -5/3 here. Okay, I'll label those at some point. But what's the next thing we have to do? Well, find the y-intercept. If it's a function, there's only one y-intercept. The y-intercept occurs when x equals, why is there only one? Because a function has a unique value for every value of x. So if x is 0, there's just one value for y. And we can see as that's true. If x is 0, we get -5 here and 10 here, which multiplies out to -50. So I'm not going to write out the details of that, but make sure you understand. It has to be the point 0, -50. Okay, so well. We have 0, -50, and we have -5, 0. And -5/3, 0. Okay. Now, if we recognize, doggone this thing. I'm sorry, there's something going on that really kind of has me angry today. Students are being terribly disserved and there's nothing we can do about it. For 2 years. Terrible situation. Okay. So I don't get angry about many things, but that one makes me angry. Okay. And I'll keep that to myself. My tone is a little bit, and it's energizing me. So we should have a good class if I can. Just something just I found out just before class. Yeah. Okay. Okay. So what was I saying before I distracted myself with something that should be irrelevant? And it's not our fault either. Okay, yeah, that's right. You got these 3 points. What's a graph that goes through those 3 points look like? Well, there are lots of graphs that go through those 3 points. Okay, there are circles that go through those 3 points because a circle isn't a function. Maybe a half circle. Okay, that'd be kind of a stretch. I think you might be a half circle there. A parabola. Could it be a parabola? Well, sure, it could be a parabola. Some of you expanded this to show that this is a quadratic function. So we know 2 things. You can find the zeros using the quadratic formula if you want to go to that trouble. Or since you have it in this form, you just find the zeros the easy way. Or, well, and then if you recognize that this is a quadratic function, you know you've got a parabola. Okay, so there's only one possible parabola, so I'll attempt to sketch it. Yeah, pretty bad, but a little wobbly there. It's something like that. Okay, now, is that really going to work? Well, we get to the next question. If x is a large positive number, what can be said about the value of y? Well, if x is a large positive number, that means you got an x coordinate out here. And if this is a parabola of this shape, you're going to have a really big negative result. If x gets even halfway big, your negative result is going to be really big. Now, how can we tell that? By looking at the expression. Well, if x is really big, then this is, if x is a really big positive number, this term is going to be a really big negative number, and this term is going to be a big positive number, right? When you multiply 2 really big numbers, you get a huge number. And when one of them is negative and the other is positive, it's a huge negative number. So, but we can answer this question. Now, I've said this a number of times, tried to get this across. Now, I'm not blaming anybody for that. Nobody's being egregiously disserved. okay? But you need to know this, okay? So we need to focus on this idea. Is that consistent with what we see here? Yeah. If this is a parabola, that's going to be that's certainly going to be true. Okay. We don't have to know that the graph is a parabola to do that. All we have to do is consider what happens if x is a big positive number. And if x is a big negative number, well, this is going to be really big, but it's going to be positive because it's a negative x. And this is going to be really big, but it's going to be negative. It's still going to be a big negative number, totally consistent with this graph. Now, these are the principles you need to graph polynomials. Okay. Okay, well, let's ask what if the function is negative x minus a times x plus b. It's going to get a little sloppy here, times x minus c. What can you tell me about the graph of this function? Using similar reason to what we just did. So we can quickly find the zeros of this function. Okay, well. Okay, well, depending on your values of A, B, and C, if my values are negative x minus 5x plus 7x minus 12, 0 occur when x is negative 5, negative 7, or 12. So we draw the graph. Here we got the 0 at negative 5, we'll put that above here, negative 5/3, and 12. What's the y-intercept? We plug in 0 for x, we get negative 5 times 7 times negative 12. That's 420. So now the y-intercept is 0, negative 420. Got to go through all these points. We can't go through the x-axis at any other point because no other value plugged in here can possibly give us 0. If x isn't equal to one of these numbers, then none of these numbers can be 0. And when we multiply them, you multiply a bunch of numbers that aren't 0, you're not going to get 0. So we can't go through the x-axis anyplace else. If x is a big negative number, we get a very large positive value of y. For large positive X, we get a very large negative value of Y. We draw a graph that has these characteristics. Okay, that means have a large positive here, we're going to have a large negative here. To the left of all our zeros, it's going to go up very rapidly. To the right of all our zeros, it's going to go down very rapidly. All we have to do is think about, well, if X is a big positive number, for example, we're going to have a negative times a positive, and they're all going to be big. You multiply three numbers, you get a really big number. Three big numbers, you might get a really big number. And if one of them is negative and the other two are positive, it's got to be negative. That means the graph is going to go down over here. Similar reasoning for large negative X. This means our graph is going to have characteristics much like this. Now, how high does it go here? How low does it go here? A little bit difficult to judge. Again, I've said before, you know, a little bit of calculus, you can figure it out. You got to know a little bit of calculus, and it's really no harder than this reasoning once you have a couple of rules. Okay, so you can actually determine the coordinates of the low point and the coordinates of the high point. So take calculus, and this could be relevant, just like we have models in business where you have a parabola and you're trying to find the peak of the parabola, like profit versus selling price. There are more complicated situations that we might encounter. For example, well, I can't give you a good example off the top of my head. You know, it'd be harder to understand because it's a little more complicated. But it could be, for example, that there is some parameter we can tweak in our business. Okay, maybe it's the price. Maybe it's how much we pay the guy that shovels coal into the furnace. Hopefully not. Okay. You know, there are all kinds of things, all kinds of parameters, and very complicated models that we can end up with. Okay, so maybe the value of this quantity, the X quantity, can only be positive, so we just ignore the rest of this thing, and we got something that kind of looks like a parabola, but it isn't. It's not going to be symmetric. And we want to, you know, maybe this is some desirable characteristic of our business, and we want to find the maximum. Well, we have to have sort of a picture of what the graph of this function would look like, and we don't want to always have to use a calculator to find it if we're trying to think of the entire complicated business decisions, the process in the context of which we have to make these important decisions. We want to have some idea of how things change. Okay. Now, ultimately, you know, we are going to use technology if the situation is appropriate to the use of technology as opposed to just general thinking, brainstorming. But in the brainstorming process, we don't want to be hampered by having to go to a computer to find out everything. Okay, we make better decisions if we understand the trends. So this is the beginning of being able to understand those things. Okay. Okay, that's a little bit of a hand-waving explanation, and I'm talking about something I really don't know, but I do understand systems to an extent. Okay, business systems not so much. Okay, well this is how we graph polynomials. We need to have the polynomial factor, and I'm not big on the process of factoring polynomials. Quadratic, yes, you should be able to factor those and solve it by factoring. Okay. More complicated polynomials, in the real world, they never factor. Okay. So I can't give you a real world example where a polynomial of degree more than 2 actually factors. I probably did one up, but I'd probably almost have to contrive an example. I don't think factoring of polynomials is an important skill. Still, we're supposed to be able to factor them, so we're going to use long division and factor at least cubic polynomials in a way that hopefully you'll know when you get to it. I don't know if I'm going to be able to justify much time in this review to that process. And I'm not going to devote a whole lot of the final to it, but you can expect to see it for some relatively small percentage of your grade. Okay. Well, once we understand how to graph polynomials, we start talking about how to graph rational functions. So now what can you tell me about this? How do we graph this thing? What's the first question we're going to ask? Come on. It's going to say good answer. Okay, so we got the answer. Well, the denominator can't be 0, and that's right, but that's not our surprise. And I'm really being suspicious or something. Okay, surprise, we got to find the intercepts. Everybody surprised by that? It's not really a surprise, is it? Okay, so we find the intercepts. Now, the y-intercept occurs when x equals 0. Now, I'm really short on board space. I'm trying to keep all these boards so I can do a quick video if time permits later and the day not in class. Just kind of a summary. Okay, how to graph this? Surprise, find the intercepts. Well, I keep writing down these variables, but I'm not going to actually ask you to do these. So maybe I should just be putting numbers in for A, B, and C parameters. Let's go ahead and use 5, 7, and 12. Okay. Y-intercept is 5 times -7 over 12, which is -84 over 12. Okay. And I can't be, I keep getting. That's not possible because it doesn't back. 5 times 7. See, when I look at 5 times 7, I actually want to multiply 12 times 7 because there's a 12 there. So, okay. Let's get it right. 5 times -7 is -35. -35 over 12. Comes out to about -3.1. Okay. Because, 12 times 3 is 36, 5 times 7 is 35. It's not 3 it's 2.9. That's not a function of my being aggravated, that's a function of my being incompetent. Okay, negative 2.9. X-intercepts. That's easy. X is -5 or X is 7, right? Because how does this expression equal 0? It can only equal 0 if your numerator is 0. Okay. And incidentally, your denominator can also be 0. Can't have 0 over 0. But numbers that make the numerator 0 aren't the same as the numbers that make the denominator 0. So that's not going to be an issue. So we can just say numerator can't be 0. And I'm not even sure what I just said. I'm not sure it makes sense. The x-intercept occurs for this function when the numerator is 0. Well, that's going to occur at x equals 5 or x -5 or x equals 7. Okay, that's kind of small. Hopefully the camera hasn't zoomed back to the orbit of the moon. Okay. Okay, now I'm going to do something about board space. Give me a second. Zero, -35/12. We've noted that's about close to -3, so we know where to put it on the graph. X-intercepts are -5, 0, and 7, 0. Okay, so let's put 7, 0 out here, -5, 0 here, and 0, -2.9 about here. So we're going to say these are the intercepts, and I need to change the scale just a little bit because of the big number I put in the denominators on it. Oh, boy, that's bad. Still there. Yeah, but sorry. Clean so we can see it. Okay. I didn't use real good insight there. Okay, we're going to put 7 about here. Means -5 will go maybe about here, and we can use a different scale for the y-axis. But it's not actually necessary to do that. If I use the same x and y scale, -3 should go about here. And we won't be able to distinguish visually -3 from -2.9. Just getting an idea what the graph looks like. Okay, so here's our graph. Now, what else can we tell about this graph? Well, what happens if the denominator is 0? Okay, well, if the denominator is 0, it's undefined. Okay. It's undefined and we generally, usually get a vertical asymptote. Unless the numerator also happens to be zero. Okay, well. Denominator is 0 means x plus 12 equals 0. So x equals negative 12. I didn't have to redo that anyways, plus 12. Okay, well, negative 12 would be out about here. X equals negative 12. Here's the line x equals negative 12. That's a vertical asymptote. You got to go through this point, and this point. Now, what about large x behavior? Well, if x is a big positive number, we got two big positive numbers in the numerator and just one big positive number in the denominator, which means we're going to get a big positive number. Okay. So do this. We have a large negative number. Well, it means that we have to go down like this on this side. Now, as it turns out, I'm not going to talk about that in this review. You guys can kind of get that out of the book. I'll probably talk about it more in class, but we're trying to lay the basic foundation. And it turns out that if we do a long division of this numerator by the denominator, we get a linear function plus a rational function. And we can talk about that, but right now, we're just going to stick with this idea. So how do we go negative here? Have an asymptote here. Well, we could say, okay, we come up through here like this. We can't do that because we can't go through the x-axis on this side of negative 12. The only zeros are here, here, and here. Can't go through the x-axis anywhere but these 3 points. So we can't come up like this and form an asymptote. It means we got to sort of go down like so. And there's our vertical asymptote. We'll talk a little bit more in class about why we get a vertical asymptote in the actual pre-calculus class. Now, how do we do this? Well, we've got a vertical asymptote here, so we've got to come down from here in such a way that we go through these points and back up. So we're going to probably do something like this. That kind of looks like I just drew a parabola, and that's not really what happens. Okay. Turns out that there's a slant asymptote for this function. But if we ignore the idea of slant asymptote, with this vertical asymptote and behavior. There's actually more to this graph. We do a long division of this into this. And it actually tells us what function we approach. Not with at the on the ends. Again, talk about that more in class. Okay, so what's the bottom line? Find the y-intercept, that's easy, at x equals 0. Find with the numerator 0. Values of x, make the numerator 0, make the whole thing 0, and those are the x-intercepts. With a little caveat. That you got to be careful that the denominator isn't also 0. Find with the denominator 0 is your vertical asymptotes. And then get the end behavior. By the way, it's stated in the text. We're going to let x go to infinity and see what happens. Tells us what happens to the far right. Let x go to negative infinity, tells us what happens to the far left. Okay. So with these two examples, or three examples, we got the basic ideas of how you graph rational functions and some insight into why they behave the way they do. Now, we had early discussion about why you get vertical asymptotes. It's because when you divide by numbers close to 0, you get big results. As long as you're not dividing 0, in which case we worry about it. Okay, I don't want to address just yet. So let's see if we can apply this to another rational function. Sometimes we use long division, okay? And we would actually with this example. Again, I don't want to confuse things at this point. Okay, so try this one. Follow the procedure. Find the y-intercept, write it down. Y-intercept is, and then write it down, because if you write out the y-intercept is, that reinforces what you're doing rather than just imitating what you've seen me do without really thinking about what it means, okay? If you write it out, it focuses your attention a little better on what you're doing and why you're doing it. So, y equals x plus 3 over the quantity x minus 4 times x plus 7. And find the y-intercept, find with the numerator 0, find with the denominator 0. Work out the end behavior and write it out, write out the ideas as best you can. Everybody has different ways of writing things out, and that's fine. Okay, so looking at this, everybody did this quite well. Systematically, you find the y-intercept. It's 0 and 3 over -28. And 3 over 28 is pretty close to 3 over 30, and 3 over 30 is just 0.1. So for the purposes of slopping down the graph, we can say that the y-intercept is about 0, -0.1. Okay, the x-intercept. -3, 0. I think everybody got that. And your vertical asymptotes are x equals 4 and x equals -7. And everybody got that much. I didn't have to do anything. Just sit back and enjoy what you're doing, okay? So that's an excellent start. Now, the long run behavior is always a little bit of a challenge. So you get the idea, and it's a hard idea for people to get. So let's think about long run, okay? First of all, for large x, well, let's just let x be quite a bit bigger than any of the numbers we get for the zeros or the intercepts. 100 is big enough because 100 is at least 10 times as big as any of these numbers, okay? So you go to a number that's at least 10 times as big as any of these numbers, that would be like 100. Yeah, nice round number, okay? If you want to think about what it would be if x equals 114.8793, you may, but 100 is an easy number to write down. Okay. Hundred is bigger, I should say, lots bigger. Actually, for lots bigger, I'd want to go to at least 1,000. It's significantly bigger, okay? Quite a bit bigger. So I've written down there where you can't read it, QAB for quite a bit bigger, okay? You don't want to let it be 12 because then you can't say, well, you can't say what I'm going to say, okay? Well, if x is 100, we get y equals 103 divided by 96 times 107. Okay, and this is close to 100 over 100 times 100. Now you might want to multiply 100 by 100, but I wouldn't do that. Now that you have the same numbers here, here, and here, you can write that as 100 over 100 times 1 over 100. That's just 1 over 100. Now, if you think through why, you end up with 1 over 100. You kind of draw a line through this and a line through this and put a 1 up here because you got to have that 1 because this is how you really get it, okay? That's why I don't like cancellation. People do it wrong. People cross out this and this, and then they'll just write 100 because they don't know what to put in the numerator, and they won't even bother putting the other 100 in the denominator. I see it all the time. So you want to be careful. Okay, well, our conclusion is if we make X be even bigger, we're going to be even closer. If X is 1,000,000, it's like 1,000,000 over 1,000,000 times 1,000,000, which is 1 over 1,000,000. It's really small. 1 over 100 is pretty small. Actually, right there is 1 over 100.1, right? That'd be 0.01, sorry. So if X is negative 100, Y is close to okay. We get this. I just wrote it down kind of sloppily, but if you write it out, you can convince yourself then and start developing an intuition that if you divide a big number by a product of two big numbers, you're going to get a really small number. And since there's no limit to how big, there's no limit to how small. Okay, so as X goes to infinity, Y goes to 0. Because the bigger the number we use here, the bigger our denominator and the smaller our fraction. Now I'm going to say as X goes to infinity, Y goes to 0, but it's always positive, right? So I say Y goes to 0 through positive numbers. That's what the positive means. And here, if X is a big negative number, you're going to get a tiny negative number, meaning Y is going to go to 0 through negative numbers. Again, why does it go to 0? Because the bigger the number you use for X, the smaller your result is going to be. I started out saying, well, use 1,000,000. Well, 1,000,000 is overkill. But you can think, okay, if X was close to 1,000,000, your numerator would be close to 1,000,000, your denominator would be close to 1,000,000 times 1,000,000, which is getting really close to 0 on both scales. Okay. So now we can draw the graph. And we don't need to meticulously scale our graph. The reason we don't need to, sometimes you do want to meticulously scale a graph, but we don't really know exactly what kind of shape these curves are going to have. We just know the approximate shape. You're not going to be able to use that graph to make good estimates. You're going to use that graph to see trends and to see what happens. As you approach the asymptotes or as X is in this range or whatever. Okay, so we can answer a lot of questions, but here we go. Okay, so our vertical asymptotes are 4, -7. Our intercept is at -3. So I can put X equals -7 here. I can put X equals 4 here. Okay. Then I can put my zeros in. Well, there's only one, it's a -3. Here's -3, 0. And then I'm going to put 0, -0.1. Now, I'm not going to use equal scales on my X and Y axes because -0.1 on this scale would be practically right on top of the origin. So I'm going to use a different scale. I'm going to say, okay, well, down here, I'll still make it kind of small. But that looks more like -1 if you have the same scale you have on the X. That's 0, -0.1. To the left, we're not going to go way down or way up. We're going to go close to 0. So on the left, we're approaching the x-axis from below. On the right, we're approaching the x-axis from above. And there's something seriously wrong here. What's my function? Never mind. I don't know what I said. Okay, so one graph that I saw is really good. Came down through here, came down through here, and it went down here. Now, why does it go down here? It goes down here because it has to approach this asymptote, and it can't go up because when you're down here, you can't go up unless you go through the x-axis, and you can't go through the x-axis except here. That's it. Now, what happens on the other side of the asymptote? Well, it's pretty simple. You start way up here, and you come way down here. You have to approach the x-axis because of the long run behavior for positive x. And same thing over here because of the long run behavior for negative x. So I don't have a lot of room to draw that, but there's a fairly good depiction of the graph. Okay. Well, that's the process. We'll continue in the actual class here in a few minutes. Now, we're going to be addressing graphing polynomial and rational functions, which is, if there's a weak spot in this course, that's it. Okay. And y'all are working too hard. You're too good to let this continue to be a weak spot if it still is. Okay. So you got 3 functions here that I ask you to just kind of graph. Give you a few minutes. Don't want to give you too much time. It's our last day. I really regret that because you've been a great class. Really love teaching this class. And hopefully, y'all will continue to do as well as you have. Okay. When I ask you to graph anything, first step, find the intercepts. It starts giving you information on the graph. Okay, so it's just like, that's automatic, find the intercepts. Now, how do you find the x-intercept? You let y equal 0. How do you find the y-intercept? You let x equal 0. I'm not going to belabor that point now because that should be second nature. But here it is, and I'll be pointing to it on one of the boards here. So when you look at this, if you do look at it from this part of your review, it'll remind you about that. That's a big deal. And then you probably want to actually write out these steps, organize, find intercepts, write it down on your paper. So if you get into the calculations and stuff and forget why you're doing them, you can look back up there and remind yourself because it's easy to forget what you're doing. Every year I get a little more forgetful about what the heck I'm doing. Okay. I think y'all are in an upswing there with working memory, but still, if I can lose track of what I'm doing, lose the forest from the trees, so can you. Okay. So write that down, find the intercepts, and then do it. Then what else do you do? Well, for rational functions, what happens is x goes to infinity or x goes to negative infinity. Once you know the intercepts and what happens as you approach infinity, you're not really home free because you got to worry about multiplicity, but we'll talk about that in a minute. Okay. But the overview is you look at what happens as you approach infinity. For a polynomial function, it'll either go up or down as you go far to the right, and the same as you go far to the left, and you got to figure out which. And then rational functions. You want to find the vertical intercept. Vertical asymptotes in a long symmetric pattern. Okay. Probably longer for you than for me, so I'm not going to complain. On vertical asymptotes, there's your start. There are some details in the middle, but that's how you start. Okay, so go ahead and do a little bit with that, and then we'll dive into just me telling you stuff, okay? But I want to get your head into the game here, because it's been a while since we talked about any of this. Okay, now I'm just going to say it, but then I'm going to show you some of the process. Find the intercepts. How do you find the intercepts? You let x equal 0, you find the y-intercept. Pretty much everybody's done that. That's pretty easy. If x is 0, you have whatever a times b times c. You got two negatives, negative a and a negative c, which is the same as just an a times a c and a b. Okay. For this one, find the intercepts. Okay. What makes y 0? Let me go back. I think I said something wrong there. Okay, here's your first function. Okay, you want to find the y-intercept, you let x equal 0. Okay, I think I said that right. Okay, so you let x equal 0, you multiply three numbers and you got it. Okay, what about this one? Find the y-intercept and you let x equal 0. It doesn't change from one function to another. Let x equal 0, it will give you the y-intercept if there is a y-intercept, because some functions don't have y-intercepts. Take the basic reciprocal and reciprocal square functions. They don't have y-intercepts. You can't divide by 0. As you approach 0, these things blow up. Okay? So you want to remind yourself of that. But in any of these, that's not going to be an issue. Okay? If x is equal to 0, you're always going to get a number. Now, if I was dividing by just x, then we couldn't do it because you can't divide by 0. Okay, can't let x equal 0 if you're dividing by x. You can, but you're going to get an undefined result. Calculator's going to give you an error. Your computer will blow up. All kinds of disastrous things will happen. Okay, so there we have it. Okay, so that's how you find y-intercepts, right? How do you find x-intercepts? You let y equal 0. Okay. Now, look up here. What value of x, how would you find one value of x that makes y equal 0? Well, it's easy to do. What you really want to do is you want to write out an equation. Set this equal to 0 and then find the solutions. And it's easy. If x equals a, this is going to be 0. It's going to make the whole thing 0. If x equals c, this is going to be 0. It's going to make the whole thing 0. If x is negative of your b number, this thing's going to be 0, making the whole thing 0. Okay? And if x is any other number, not one of those three numbers, then none of these are going to be 0, and you're not going to get 0. That's fundamental. Okay? On this one, how are you going to get 0? Well, you're going to get a fraction for any number. The only way a fraction can be 0 is if the numerator is 0 and the denominator isn't. Okay? course, the denominator is 0, it's not defined anyway, so it's not an issue. Except you want to recognize that. So you set this equals 0, it's going to be 0 only when the numerator is 0. Okay. Down here, I'm going to have one number that makes it 0. That'll be negative whatever a is. That'll make the numerator 0. The denominator won't be 0. So that's going to be a 0. Okay. So the principle is find the intercepts. Find the y-intercept by letting x equals 0. You find the x-intercept by letting y equals 0, and you write out an equation for each of those. Now you can kind of bypass that if you're sure of your habits. But when you're doing this, especially for review, you kind of want to do that. When you do it on the exam, you kind of want to do that because people are not real secure with this. Okay. And it's something you want to be secure with when you come into the exam, because it is going to count fairly heavily, since we kind of omitted it from the midterm. Okay. Then you do the long run behavior. I say x goes infinity or x goes to negative infinity. You think about what happens if x is a huge positive number. If x is a huge positive number, you're going to have 3 huge positive numbers here. If you multiply 3 huge positive numbers, you get a humongous positive number, which means that as x gets big, y is going to get really big really fast. The graph's going to go up like this. Okay. Now, and always with a polynomial function, the graph is going to go up or down on this end, and it's going to go up or down on this end. I think I already said that. Okay, but that's why. Okay, and now what about this function? Well, it gets a little more complicated. In this case, you'd have 3 big positive numbers on the top and 1 big positive number on the bottom. What happens if you multiply 3 big positive numbers and then divide by 1 big positive number? Basically end up with 2 big positive numbers multiplied. It still gets huge. Okay. What about this case? You would end up with a big positive number over a big positive number in this case. What happens if you divide a big positive number by a big positive number? You approach a constant number. Okay. And let's talk a little bit about that. Make sure that we understand it. So continue with your work. Just kind of try to sort out as many of those steps as you can, and then we're just going to lay it out, because we don't want to take a lot of time in class. We've already taken 25 minutes. We want to give you a good summary that you can look at and see in a fairly short time what needs to be done. Okay. Okay, now let's going to do this. I've given these functions names, F, G, and H, so I can talk about them. Okay. I don't want to write out all this when I want to talk about F. I don't want to write out all this when I talk about G. I've got it written down. That's all I need. Okay. X-intercept. Happens when y equals 0. It's worth making note of that, right? Y-intercept occurs when x equals 0. Okay, well, let me also plug in numbers. Actually, I'm not going to plug in numbers. I'm just going to use A, B, and C. Okay, so you know if your numbers match because you use your own numbers. Okay, x-intercept y equals 0. So this is at A. Negative B and C. That clear? Whatever your numbers are, if x is A minus A is 0. If x is negative B plus B is 0, and so forth. Okay, well, and then we can apply the same thing down here. The only way it can be zero is if the numerator is zero. If you don't totally understand that, you need to write it out. Go back and look at the video, write out things that I'm telling you to write out, advising you to write out. I don't require it. I think you'll do better if you do that. Okay? So you're going to get what, C, negative C, D, and your A number. If you read this as an A, this board's a little rough. So is my handwriting. So put the two together, you might not be able to read it. That's it. And it should be clear enough on the video if you check it out. Okay. The y equals h of x plus a. That's the only way this can be zero. So the numerator is zero. So the only zeros at your A number. Okay. So there's information we can put on the graph. We just take A, B, and C here. So we got negative B. We've got A. And we've got C on the scale. I could say negative B 0, A 0, C 0, but I'm writing small on a rough board. I don't want to write out both coordinates because I think we understand what we're seeing. Okay, now what about the y-intercept? You let x equal 0 and you get A, B, C. Those asterisks are a little bit, I'm going to use parentheses. Those asterisks come up pretty rough. I don't want anybody to be too confused by that. And this is multiplication. Okay, it's not, this isn't listed separately. I just didn't have the foresight to myself enough room. So I think we understand that. You multiply A by B by C. And of course, I think almost everybody got that in the first thing. Okay, on this one, it's negative C times D times A divided by negative B, if we let x equal 0. And of course, you got negative and negative, so you can just kind of, okay. We don't need to write the two negatives, okay? I think everybody understands that. And down here, it's just going to be A over C for the H function. So x is 0, that's all we've got. And it's negative. And I'm writing it out kind of small, but you see the pattern that goes over these three fairly different functions. X-intercept and y-intercept, though, are equally straightforward in each case. As long as you remember the only way a fraction can be 0 is if the numerator is 0 and the denominator isn't. Okay, vertical asymptotes. No vertical asymptote. Guess how do you get a vertical asymptote? It's just like 1 over x. As you approach x equals 0, you get bigger and bigger numbers. Okay. No example of vertical asymptote occurred to me yesterday when I was going over to the testing center to pick up a test. Walking down the hall. Imagine walking down a long hall. Okay. And halls, the walls over there, infinitely long hall. take a long time to walk all the way. Okay. Now, if door's over there, then from that point, a path from where I am to that point makes a right angle with the wall. Okay. So my angle with the wall, with that point on the wall, is kind of like 90 degrees. Now, I walk a little further forward, and what happens? I don't want to get too close because the camera, now the point's back there. Angle's less than 90 degrees, right? We got an acute angle. Now, what happens if I keep walking? The angle keeps getting smaller and smaller and smaller. Everybody visualize that okay? If not, walk down a hall and every once in a while look back at the water fountain. What angle is your line of sight making with the wall the water fountain's on? Okay? Right there, pretty long hall here. And you see pretty soon your angle is approaching zero. Okay? Asymptotically, because no matter how long the hall is, the angle never really is zero. Okay? Another example of an asymptote. So you maybe keep that in mind a little bit. Okay, so vertical asymptote, there is none. Now over here, there is a vertical asymptote. It's the wrong symbols. X equals whatever your B number is. And this one has a vertical asymptote at X equals whatever your C number is. Because as X approaches B, your denominator approaches zero. You're dividing by zero, which means you're dividing by a smaller and smaller number, which means your answer gets bigger and bigger. Okay? Same thing here. All right, so here we've got a lot of characteristics of these graphs. Now, there's also long run behavior, but let me just on another graph here. That depicts this situation. We've got like negative C. And then we've got A. And we've got D. Those are our zeros. The graph has to go through these points. Can't go through the x-axis at any other point. We've got our vertical intercept, which in this case is something I don't want to try to write on a compressed board, but it's positive. So we have a positive vertical intercept. And I could label it, you know, C times D times A all divided by B. Okay, it's a fraction. It's going to be probably a pretty big number. If A, B, C, and D are all kind of around the same size, most of them are single digit numbers, none of them are really small. If it's double digits, not a big double digit number, so they're in the same ballpark. So you're probably going to get a fairly big answer in the tens, maybe even as much as 100. Now, vertical asymptote, we got to do vertical asymptote. X equals B. Well, B is between A and D, is the way your numbers are structured. So everybody would have a vertical asymptote between these two zeros. That's the way it's going to look. Then you do your long run behavior and you learn stuff. You got to have your long run behavior before you see the overall picture. I'm not going to do the long run behavior yet. Get this much down on a test. Get this much down, well, you're probably not even going to get half credit if you don't consider long run behavior and draw some kind of reasonable graph. It may be close to 4 points out of 10. Okay, because I know you're following a reasonable procedure. It's one of the things we want to teach in this course. You're thinking, you're executing that much of the procedure correctly. I might even be generous and give you half credit. I don't know. But I want to see the long run behavior. I won't give you over half credit unless you do all of this. Okay, do bits and pieces of it. Depends how many bits and pieces. Okay, that's for this function. This is for this function. I could label it, but I don't want to label it. Wherever I label it, I know the graph is going to go through that point, whether I want it to or not. Okay, so I'll label it a little bit later. Down here, this one is actually a little simpler. You got your y-intercept, which is negative a over c. So you're going to put that below the x-axis. And then when you figure out what the number is, you'll label your y scale accordingly. Don't start with your y scale, because like if you put a y scale from negative 10 to 10, and this asymptote or this 0 occurs at 0.003, you're out of luck. Okay, you want to scale it so that you can see that point. Then that's the y-intercept. The x-intercept is at a. And your vertical asymptote is to the right of that. Everybody's would be to the right of that, because C is bigger than A. Okay. So right there is a lot of information. Now we have to know how to use that information to construct a graph. Let's look at the long run behavior. As x approaches infinity, in this case, that means x is going to be a really big number. You're going to have 3 really big numbers. It's going to go up really fast, right? The y value is going to go up really fast. If x is even 100, then for your numbers, every one of these numbers would be at least 80. So you'd have at least 80 cubed, which is 512,000. Okay. So if you've got 80 units, if this is 80 from here to here, where's 512,000? It's at least up in the clouds. Okay. So as x goes to infinity, I'm not going to write out that y goes to infinity because that doesn't tell you everything. Y really goes to infinity because that's if x is 100. If x is 1,000, every one of these numbers is at least 900. Okay, what's 900 cubed? Well, it's 729 million. Okay, everybody knows that, right? Okay, almost a billion. Now that is out of the atmosphere. Okay. So what you can do is you can just kind of say, okay, as x goes to infinity, the thing is going to go way up. Okay. And what if x goes to negative infinity? We might as well do that while we're talking about this function. That means x is a big negative number. The numbers we're using, none of these numbers is over 20. Now, you know, A, B, and C are all less than 20. A lot of times they're all less than 10, but let's say B says they're all less than 20. It means all these numbers are going to be at least negative 80. And you cube negative 80 and you get negative 512,000. Okay. And you can play around with the numbers like that. So that means it's going to go down like this. And there's a depiction of your long run behavior. So when we put this graph together, and I'll do it separately here, a little bigger graph so we can actually do it. Here's your f function. Here's your G function. Here's your H function. Okay. Now, what about G of X? Well, again, X is 100. Each of these numbers is at least 80. This number is not over 120. Actually, it's going to be less than 80 because of the negative there. But they're all pretty close to 100, aren't they? So your answer is going to be pretty close to 100 times 100 times 100 divided by 100. Well, 100 times 100 times 100 divided by 100 is 100 times 100, right? It'll be a big positive number. So again, say, okay, we can draw a picture. Big positive number here. And as X goes to negative infinity, well, you're going to have a big negative number and a big negative number and a big negative number divided by a big negative number, right? Just like, say, negative 100 times negative 100 times negative 100 divided by negative 100. How many negatives you got? You got 4 of them. It's going to make your result positive. You got 100 up here, it can be divided by 100 down here, and you're still left with 200, so it's going to be there. It's going to be positive. So it's not going to go down over here, it's going to go up as you go to negative numbers. So that's the overall graph of this one. So overall, this graph is going up here and down here, just kind of like a cubing graph. This one is going up here, and it's also going up here, which is a problem. That will work out in a minute. Which is just kind of like a parabolic graph, but yeah, it wiggles around some in the middle. Okay, this one. Okay, well, if X is a really big positive number, then X is 100. Then this is pretty close to 100. This is pretty close to 100. This is pretty close to 1. Okay. If X is 1,000, you can say pretty safely, but since none of these numbers are bigger than 20, this is somewhere between 980 and 1,020, and so is this. Well, even if you divided 980 by 1,020, you could be pretty close to 1. If you let the number get bigger and bigger, the A and the C matter less and less. Like 1,000,005 divided by 999,991, okay, is pretty close to 1, real close to 1. If you got a picture of what division means, you understand that. Otherwise, take my word for it, your calculator won't lead you to that insight. Which is one of the big problems with people being trained on calculators. Okay, so here we have it. So what happens is this, whether X is positive or negative, got a big positive, it's positive divided by positive, and the numbers are about equally big, so it's about 1. If you got a big negative divided by a big negative about the same size, you're going to get something close to 1. So you're going to approach 1. So Y is going to be close to 1 as you get out this way and this way. And that's at both plus infinity or minus infinity. So what are these graphs ultimately going to look like? You know, a little bigger picture of this. You also have your x-intercept. So your y-intercept, which is a times b times c. I thought that I'd drawn that, but I didn't. It's going to be positive. And now I can label this point. Actually, this is negative B0, this is A0, and this is C0. I didn't have room to write the zeros here. And this, I'm not going to label it just yet. I want to see where my curve goes, but now it has to go through this point. But it's going to be A times B times C. Okay. And that might be a pretty big number. Could be in the well up in the hundreds. Okay. Then we know that at the right it goes up like this. Now this is well to the right of any of the zeros. Because remember the number that I used was like 100 on the scale of the numbers that you're using. Okay. And 100 is well a whole lot bigger than any of these. So we'll get out a whole lot bigger than these numbers to the right of these numbers. It's going to do this. And we get out way to the left of these numbers, it's going to do this. Well, then it becomes pretty easy to draw a graph that represents that behavior. Your graph is probably not going to be overly accurate until you take a calculus course and learn where the peaks and valleys go. It's easy once you learn a little bit of calculus. Okay, it's one of the easier things in calculus. The polynomial functions. For other functions, it can be a pain. Okay, so that means we're going to kind of come up here. And we got to go down through here, kind of level off and come back up through here. I don't think that's a very good graph. I don't like that shape there, but you get the idea. Okay. So here is your f of x function. A reasonable depiction. Using your numbers, it's going to shift these points right or left a little bit, but it's going to have this overall shape. And now we can label the axis here, and it's going to be zero, comma, product A times B times C. And you can multiply those numbers out. Okay. The G function. Well, let's copy down what we already know. You've got a point here and a point here. This is A. This is D in a vertical asymptote at x equals B. And then you have your C over here. We have a y-intercept, which is up here. We don't label it just yet. Get the curve, then figure out where you put your label so the curve does go through the label, like I don't. We go up when we get out that far to the right here. We go down when we get out far to the left here. And that's pretty much all we need to know. It means then that we come up through this, kind of like we did over here, and then down through our y-intercept. Then down through the point where x equals A, or with the intercept at A0. And then the question always is, do we approach the asymptote upward or downward? Okay, so positive asymptote or negative. That's not really good terminology because it deals with both sides. Is the approach from here? Do you approach through negative numbers or positive numbers? It's got to be negative numbers, because if you go up here through here and down through this zero, you can't get back up because there's no place to go through zero. Remember, this thing can only be zero if x is negative C or D or negative A. Any other number is not going to give us zero for any of these factors. We're not going to multiply out the zero, and you're not going to get y equals zero, which means you're not going to have a point on the x-axis. Okay. Now, what do we do On the other side? Well, I've got a conundrum here. There's something to work it out. And I think we got somebody willing to straighten me out on this, so let me pause and get that input. Okay, so I've got an error over here. First of all, it's pointed out that x equals negative a is going to be a 0. Okay, so my a is on the wrong side. I'm going to have a negative a. So let's fix that over. Because my error was making it impossible for this curve to do what it needs to do. Okay, over on the left, it has to come down from up here. And it doesn't have any place to get through 0 to get up to this, which is really not a good thing. Okay, it can't be right. So I knew there's something wrong, and I'm glad somebody saw it as quickly as they did. Okay, so this means that my point over here has to be negative. It might be hard to read. There it is. Which means that I probably need to just redraw this whole picture. I'm trying to modify what's been built incorrectly. And let's see, other things. I think my y-intercept is still good because x is 0, I'm going to have a negative from this, negative from this, these are going to be positive. So that's going to be okay. So I think everything else is kind of okay. And I think we can work with this picture. Okay, because we've got to come down as we come in from the left. We go down through this 0, up through this, and up through this, right? And then we go on up to our asymptote because we can't get back through 0. Then on this side, we're going to come up from down, go through here, and then we're going to go on up. Match this, it's not bigger so we can see it. Okay, so we have this point. Which would be your D0 over here. We're going to have negative C 0. And we're going to have negative A 0. I'm going to label that after I draw the curve. And then we have our y-intercept. Okay. Which I could safely now that I figured out where the curve is going to go. I'll safely label this as 0. Now I can't be too long. I'll label it over on the other side. Okay. Now we're going to wait like that. Okay. And we've got our vertical asymptote still at x equals b. Now we've got our long run behavior, which goes up to the right and up to the left for reasons we worked out earlier. Now we've got to come down from here, go through this 0, back through this 0, and up through here. We've got to go through all 3 of these points. Can't go through the x-axis except at these points. Have to go through the y-axis at this point, so it's going to come down. I don't like this. And then up here. Probably won't be real symmetric. It's not a parabola. We're away from parabolas here. Okay, on this side. we've got to go through this point and up, going up. That tells us that we've got to come up from down here. Okay, so probably going to come up and do something like this before it takes off. There's our graph. Now, if you make a mistake like I just made, you just can't get the graph to do what it ought to do, don't just slop down any old thing, say, man, this graph isn't doing what I think it ought to because. Okay? Then I'm probably not going to penalize you a whole lot. Say, oh, yeah, you got a wrong sign on this 0. I did. Okay? And now it's not working and you recognize that, but you're not sure how to fix it because you haven't been able to see the error that you believed when you made it. And it really is hard. Okay, I don't expect miracles, but I do expect basic competence, okay? And yeah, y'all have been meeting that expectation ever since we started this course. So hang in there another week or less. Okay. I need to check something. See what you can do with the third one using your own numbers. Yeah, I think we just barely got it on the camera. But it looks slightly bigger copy of this with A to the left because the intercept is negative A. The far right and far left behavior in this case is we approach y equals 1 as a horizontal asymptote. Doesn't go off to infinity because the numerator and the denominator, as x gets bigger and bigger, have practically the same value. When we divide one by the other, we get something very close to 1. So y values have to approach 1, which is what I kind of indicated with this picture. So what happens is way out here, y is equal to 1. So we just stay pretty close to the asymptote until we get here. Then we go down through the intercept here, and eventually we angle down and hit the vertical asymptotes. On this side of the asymptote, again, I'm missing there. The vertical asymptote is x equals c, not b. In any case, you got to be above the line y equals 1 because the numerator for big X is always a little bigger than the denominator. Okay, so this number is always a little more than 1. And as you get close to C, this number is still going to be positive, but this number is going to approach 0. So you're going to have a graph that looks like this. Okay. So that's pretty much it for these. And I'm going to kind of quickly talk about multiplicity of zeros. Okay, very quickly, the thing that changes when we get this square in here, so now this is your k of x function, we can use the same graph we used for the f of x function. This is your graph of f of x. This is p of x. This is h of x. Now, the f of x function, the thing that changes here is your far left behavior. As x approaches negative infinity, you now have two negative numbers here. And one here and one here. That makes four negative numbers. You multiply this by itself, then by this, and by this. Four big negative numbers give you a positive, which means that the thing has to go up here. And it has to go up here. But how do you get down here in order to go through here? If you go down through this, you can't get up here because you can't go through the x-axis between here and here. You don't get to go through the x-axis till you get over here, and you can't go around here and come back and loop around. That doesn't work at all for many reasons. Well, what has to happen is you have to come down here. And then right here, it sort of behaves like a parabola. And then it comes up through here. And then it can go down through here and up through here and on up. Okay. X minus a quantity squared is a quadratic function. It's got a parabolic graph with a vertex on the line x equals a. Okay. As a matter of fact, at x equals a. Oh man, I'm changing this. Okay. I'm going to put the square on b. I was just careless when I wrote that. Okay, that's negative b0. Okay, well now it works. Okay. Makes sense? Okay, very good. Of course, you're going to need to review examples to get good at this. So I'd go back through the entire assignment, try to understand it in all the detail, all the multiplicities and stuff, and how long division can be incorporated to find slant asymptotes, which the relatively minor part, but we talked about it a lot in class. So you don't want to ignore that. Although long division flummoxes you terribly, well, it's going to cost you, but you can live. Okay, you've been a great class. Sorry for the confusion here. Something came up before my first class, right? I had these formula sheets, which got distracted a little bit. You will have that formula sheet on the exam. Okay, so there are formulas you don't have to memorize. Some of those I prefer not to put on there, but we're doing an assessment in conjunction with the exam, and that's what the department agreed on. You pretty much knew it all when you did the midterm. But you need that crutch, it's going to be that. Okay, great. Again, really enjoyed the class. Y'all have been wonderful.